Welcome to this problem solving session, week 2 of this NPTEL course, Numerical Methods, Finite Difference Approach. So, we'll be solving assignments of assignment 2 of previous year. So, that will give like that will help you to solve this year assignment also too. Because that will be covering the lectures from 6 to 10, from which effectively the assignment 2 is being asked this year also. Okay, so the first question, in the explicit scheme, when solving parabolic equation, t by del x square, the partial derivative are replaced as time derivative by forward difference. Fd is forward difference, CD is central difference, BD is backward difference. So in explicit method, what we do is for time we replace it by forward difference, and for the space derivative, what we use is the central difference. So option A is the correct answer. So what we can write is so if we write is like this, so this represent the space, this represent the time. So we can write it u I j plus 1 u I j delta t u I minus 1 j to u I j plus u I plus 1 j and delta x square, because this is central difference. So that will be of order delta t plus of order delta x square. So this is forward difference, and this is represented by the central difference. Okay. So question 2, using explicit scheme, the value of u for this equation, the equation with the boundary conditions are given and the initial condition is given. To consider delta x is 0.25 and delta t is 0.02. We need to find the value of this. So delta x is 0.25 and delta t is 0.02. So if we consider I equal to 0, then x equal to 0, I equal to 1, x equal to delta x, that is 0.25, and for j equal to 0, t equal to 0, and j equal to 1, t equal to delta t is 0.02. So effectively we require, if we represent this like, we require u comma 1 to find out. Right, so that is effectively 0.25 and 0.02. So we have to use the explicit scheme. So for the explicit scheme we can, so for that, first of all, we know what is the value of r. R is delta t by delta x square, so it will be 0.02 divided by 0.025 square is 0.32. So now explicit scheme. So from the explicit scheme we can represent it that I j comma 1 to r u I 1 minus 2r u I comma j plus r u I plus 1 comma j. So so this is the question. We need to find the value of u, which is given by this partial difference equation, dependent on first derivative of time and the second derivative of space. The boundary conditions are given, and since we have a time thing, we need an initial condition that is also given, and we need to find at x equal to 0.25 and 0.02 time. So for I equal to 0, x is 0, and I equal to 1, x is delta x, so it's 0.25. For considering j equal to 0, t is 0 initially, and at j equal to 1, t is delta t, so it will be 0.02. So effectively we need, if we represent this as the dependent variable u I comma j, so effectively we need to find 1 comma 1 for x equal to 0.25 and 0.02. So first of all we find out the r value. So this is delta t by x square. So then we know the explicit scheme. So now if we put the r value here, it will be 0.32 ui j plus 0.36 ui j plus 0.32 ui plus 1 j. Now we require what to find out? 1 comma 1, that is the thing that we need to find out. So for that we have to put I equal to 1 and j equal to 0. So if we put that 1 comma 1, it will be 0.32 u01 u00 plus 0.36 u1 comma 0 plus 0.32 u2 comma 0. So we are just replacing I equal to 1 and j equal to 0 because we require this 1 comma 1 here. So now we need to find this values u 0 comma 0 u1 comma 0 u2 comma 0. So these are like the values of the dependent variable at the initial times, because all are at zeros, right? So now the initial condition that is given is u x comma 0 is 1 plus 2 x square. So if we use that, u I comma 0 is 1 plus 2 x square. So if we put u 1 comma 0 or 0 comma 0 here, that will be u x equal to 0, t equal to 0. It will be 1 plus 2 into 0 square equal to 1. Then u 1 comma 0, it will be u x equal to delta x, u equal to 0. So 1 plus 2 into delta x square. So this will be 1.125. Similarly, u 2 comma 0 will be u x equal to 2 delta x, t at 0 equal to 1 plus 2 into 2 delta x square. It will be 1.5. So if we put the values here, u 1 comma 1 will be 0 0.32 into 1 plus 0 0.36 into 1.125 plus 0 0.32 into 1.5 equal to 1.205. So 1 comma 1, that is actually u at x equal to 0 0.25 and t equal to 0.02 is 1.205. So option B is the correct answer. So the next question is, it asks explicit scheme is stable if we can find that in lecture 7 probably. So if we take u x comma t as a function of x and t, then this we can represent it at this we can write as alpha t into some space function u x plus b into minus I beta x. So we can consider our dependent variable function of this form. Now we know the explicit scheme. U I comma j equal to r u I minus 1 j plus 1 minus 2 r u I comma j plus r u I plus 1 j. Now the error formula, if we write for this explicit scheme, let's write is E PQ plus 1. Let's replace this as P and Q are E P minus 1 Q plus 1 minus 2 R PQ plus R E P plus 1 Q. So this is the error formula. So now we'll see this, since this error formula, this error is same as this U, so we can expect this error will also be of the same form like this. So E PQ is e to the alpha Q delta T e to the I beta Q delta X. So now if we put this equation, so if we put this equation in this solution in this error formula, so what we'll have is means if we do all the algebra, what we'll have is E alpha delta T is 1 on the form 1 minus 2R 2 sine square beta delta X. So this is covered in lecture 7. I am just writing that thing. Means for more detailed calculation you can refer to the lecture 7 in the of the. So for now for this like in for the solutions, this error term should decrease. Hello. Yes. Yeah, good evening. Hello. Yeah, I am hearing. Can I can speak up?
Good evening, sir.
Yeah, good evening. I am hearing. Can you speak up?
Hello.
Yeah, I am able to. Hello.
Good evening, sir.
Yeah. Hello.
Your voice is hearing.
Okay. Okay.
Can't be able to.
Yeah, you are able to hear me now.
Now only I hear you, sir.
Okay.
Before
Okay,
that
sir.
it is unmuted.
Okay. Okay. I actually there was no one, so I didn't know that I was unmuted.
Okay. Now only I got the signal that join now.
Okay. Okay. Fine. Thank you. Okay.
My name is Dr. G. Devika from Chennai, sir.
Okay. So I just started solving the assignment 2 of the previous year.
Okay, sir. Finite difference approach.
Yes, yes. So this so you are enrolled in the course.
Yeah, sir.
Okay. So this assignments will be like more or similar to assignment 2 of the current year also. So that will help probably. So
Okay. Just to go through the assignment.
yes.
So it is because this worksheet you have to do it is using the calculator only, most of the things you have to work out it. Otherwise you can't able to be easy to solve it now, I think so.
Some of the problems, yes. Ultimately, these numerical methods you have to implement it through
Because
some
we are now
codes.
not
So
using in the engineering classes, sir.
okay.
That is a Frank-Nicholson method, Taylor series,
Okay.
modified Euler's method, Renzi-Cotta method, then Newton's forward formula, backward formula, everything was taught that example for engineering oriented studies by using the calculator only.
Okay.
It takes time to do all the things.
Yeah, it will
Here
take.
we are giving options only. But for that options you have to do for doing this. The calculator is not using for doing part.
I am not sure. Like in your final exam, they will allow or not. I am not sure about that.
Because the previous that is not allowing the calculator. That is in system adapted
Okay.
the calculator.
Okay.
That calculus only you can use it.
Okay.
But it takes time to do that problem because what you are teaching the problem in the assignment, no? That
Yes.
is entirely different from the format. So you have to learn so many things to do all these things. Not only this part of it. So apart from that, you have to learn so many things.
I don't know about the final exam, but the assignments will be more or less same like this because these
That's why
assign,
I'm saying,
yeah, because
what
the
the
assignments that I
assignment is
am
okay,
doing
sir.
right now,
What the assignment is okay.
yeah.
But in the exam, no,
Mm.
that model, what you are starting this model, no,
Okay.
that is entirely different from that.
Okay, that I can't help because what we are
Okay, I
instructed,
know it.
yeah.
We have to learn, apart from that, we have to learn so many things also.
Yeah, that's the
So
more,
that's why you have to learn
that's
more,
what the course is
more
for.
time to do that.
Yeah, that's what the course is for. You have to
Yeah,
put in
that's
some
why.
more effort.
So
So
that's why
you
because
won't
this is
get,
short duration, no?
yes, yeah.
This is short duration. So we are working. So our work also, academic work also is asking so many things, and this is also is there. And we are practicing in between time. We are practicing everything, but at the time of we can't mind if you not open the course, write the answer.
Okay.
It is difficult to do.
Yeah, this type of course will like requires a lot of practice because this numerical methods.
Yeah,
It's
because
so
this is helpful to doing
okay,
the research
yes.
purpose.
So we have to put a lot of effort. Yes,
Yeah,
that
yeah.
requires.
So that is why we are
Mm.
joined over there to do all these subjects. Because
Mm.
this is helpful to the how to do the research in the what you are doing.
Yes, yes. Okay.
For that purpose, you have to learn it. But we
Okay.
have to learn deeply.
Yes, yes.
That's
Yeah.
my concept.
Okay. Okay, you can be there or means I will go. I mean, I will go through the
Yeah,
assignments.
you
You
go
can.
through.
Okay.
That is why I
Okay.
asked. I want to not hearing your voice. That
Okay.
is why I asked
Okay.
all you.
Yeah. Thanks.
No, you carry on.
Okay.
Thank you very much. Thank you.
Okay. So now where we like we want this stability to like what does stability means like the error it converges. So the error should die down. So for that, this term has to go. It has to be less than one, and then only the error will not propagate further. So for that, so for stability, what we require is the this term, the magnitude of this term has to be less than one. So now we have this e to the alpha delta t. So 1 minus 2 or it will be 4 r sine square beta delta x by 2 less than 1. So now using the property of modulus, this will be minus 1 less than, so this term has to be in between minus 1 and 1. So now if we take the two equalities, so let's take the left inequality. And there is another equality 1 minus 4 sine square. So this term is anyway greater than 0. So this equality will always hold. Since sine square beta delta x will be greater than 0. So and there is a minus sign here. So minus of a positive term will always be less than 0. So this will be equality anyways. It will be holding. For this, what we'll have is r should be less than 1 by 2 sine square beta delta x by 2. Now, what will be the minimum value of this? So this, if this is we know sine x is less than 1, right? Less than equal to 1. So this minimum value will be when sine s square, the term will be the maximum. So it will be 1 by 2 into 1. So r should be less than half, then only this equality uh, will hold. Like the right equality is anyway uh, being fulfilled. The left inequality will only hold when r is less than half. So this option 3 is the correct answer. Question 4 is asking the implicit scheme for solving this PDE del. So we have used Cranks-Nicholson method for solving this implicit. We term it that's a implicit scheme. So or no, Cranks-Nicholson because is one of the implicit scheme. But for the implicit scheme, what we do is we take the time derivative uh, by backward difference and space derivative as central difference. So how does feels like if we represent I comma j, this is as the space derivative and this is a time derivative. So if we represent it like so u I j comma 1 minus u I comma delta t, and then u I minus 1 j plus 1. So for that what we have is at a first difference in the time and second difference in the space. So you will see here we are representing this time derivative at j plus 1 node. Like if it was an explicit scheme, this would have been this is implicit. For explicit, ui j to ui j plus ui plus 1 j. So now, so we are representing that at the j plus 1th node. So if we represent now, which one, like here r is delta t by delta x square. So if we rearrange the terms, option B will be the correct answer here. So you can yes. So these were all covered in the lecture 6 of implicit methods. So then the fifth question is, for the Crank-Nicolson scheme, the point of discretization is, so for the Crank-Nicolson scheme, we discretize as the midpoint of z and j plus 1th node. So we have this del u del t equal to del square u del square. So we have this ui j plus 1 minus ui j delta t. Now here for the implicit scheme we represent as I comma j. For the explicit sorry, for the explicit we represent as I comma j, and for the implicit we took at I j plus 1. Now for the Crank-Nicolson, we take at the average of j and j plus 1th node. So what we have is we write at first this is at the jth level, and then we'll write for the j plus 1th and taking an average of the two. So this will be also our order of delta t and delta x square. So here option j plus 1 half, option C is the correct answer. We don't do at j or j plus 1, we do at j plus half, means at the midpoint of the j and j plus 1. Uh, so two questions earlier we saw like what was the condition for the stability of an explicit scheme. So now this asks like what is the condition required for the stability of a implicit scheme. So again we can so this was covered in probably lecture 8. So what we have in the implicit scheme, we minus r u minus 1 comma j plus 1 plus 1 plus 2 r u I j plus 1 minus r u I plus 1 comma j plus 1. So this is the implicit scheme. So now then if we take the error term like we took in the explicit scheme, alpha q delta t into e to the power I beta q delta x, this error of this form, because we saw the error and the solution of the will be of the same form. So now again if we put this here, so like the error will be of the yeah. So what we'll have is okay, so I'll not do the algebra because these are all being covered in lecture 8. So what will if we put all these terms here, so what is being required is this term for stability, this alpha delta t, as the time progresses this has to die down. So what we have, alpha delta t is of the form 1 minus 2r sine square beta delta x by 2 1 plus 2r sine square beta delta x by 2. So we get this e to the alpha delta t, the error form in the time of this form. So now for stability this e to the alpha delta t has to be less than 1. The magnitude of this has to be less than equal to 1. Now if we see here so this is what we get. So now if we take the inequalities, so this has to be if we break the modulus represent the modulus term here. So now let's take the inequalities what we have. Let's take the left inequality minus 1. So this will be anyways b equality will be
So 1 plus 1 plus, so 1 plus
yeah, I'm just taking this
you have to cross multiply.
yes. So this equality will anyways hold. Then if we take the right equality, So this will give us 4r sine square beta delta x by 2. So this will also hold for all values of r. We don't need to put any condition because sine square is anyway greater than um, 4r. Yes. So this will hold as long as r is greater than equal to 0, and that will always be greater. R is always greater than equal to 0 because it is defined as delta t by delta x square. So since r is greater than equal to 0 and sine square is also positive, so this equality will anyways hold. Here also we see that equality is anyway holding because it will give us 2 greater than equal to 0 once we do this. So the implicit scheme hold is stable for all values of r, and that's why actually implicit scheme is more preferred in many of the cases, although it takes more computational time. Like we cannot directly solve it since we are taking it z plus 1th in term. So if the system becomes nonlinear, that becomes means you have to take some other methods to solve the nonlinear system of equations in the implicit scheme. So computation time goes high, but it ensures that the system is stable for all kinds of R. So that's added advantage. So moving on. Using Crank-Nicolson scheme, the value of this u for again this form of partial derivative, the boundary conditions are given and the initial condition is given. The delta x is 0.2 and delta t is 0.08. So first of all, r is delta t by delta x square. So that is 0.08 divided by 0.2 square. So this is 2. Now at if we represent I comma j, so I equal to 0, x is 0, I is 1, x is delta x, and that is 0.2, I is 2, x is 2 delta x, and that is equal to 0.4. Similarly, if we take j equal to 0, t equal to 0, j equal to 1, t is delta t, and the delta t is given as 0.08. So what we require to find out is u x equal to 0.4, t equal to 0.08. So effectively what we need is u 2 comma 1. So this is the thing we need to 2 comma 1 we need to find the value of the dependent variable. So we have to use the Crank-Nicolson scheme. So let's write the Crank-Nicolson scheme first. So this is of the form minus r u I minus 1 j plus 1 plus 2 1 plus r u I j plus 1 minus r u I plus 1 j plus 1 equal to u minus 1j plus 2 1 minus r to u j plus u I plus 1. So you see in the left hand side we have all the variables at j plus 1th time interval, and in the right hand side we have all the u represented at the zth time interval. Let me check if I have made any errors here. Okay. So now we have to find, let's put I equal to 1. No, first of all, we need to see about how the equation is being, the problem is being defined. So what we have, the boundary condition u 0 comma t is 1, u 1 comma t is also 1. So that says that u 0 comma t is 1 and u 1 comma t is 1 effectively, or like say this t is represented as j. So this is 0 and this is 1. We are dividing delta x is 0.2, so we'll have 0 0.2, 0 0.4, 0 0.6, 0 0.8. So this is I equal to 0, I equal to 1, I equal to 2, I equal to 3, I equal to 4, I equal to 5. So I 0 comma j is 1 and I u 0 comma j is 1. That is being the boundary condition. And at 1 also it is 1. So 5 comma j is also 1. So these are the boundary conditions that are given. Then the initial condition that is being given is u x comma 0 is 1 plus 2x 0 x 1. Okay. So if we check here u 0.4 comma 0, that will be 1 plus 2 into 0.4, it will be 1.8. u and then u 0.2 comma 0, that will be 1 plus 2 into 0.2, it will be 1.4. Then u 0.6 comma 0 will be 3 minus 2.0.6. So 3 will be 1.8. So we see here these two values are equal. So what we have is these two at the initial, these two are equal, and then we have here x equal to 0.5. So these two values are also equal. Again, if we check 0.8 comma 0, that will be 3 minus 2 into 0.8, that will be 1.4, and these two values are equal. So what we can say is the initial condition is symmetric, right? Around x equal to 0.5, and the boundary conditions are also symmetric. So I'll just write, so these are the boundary condition that is symmetric around x equal to 0.5, and these are the initial condition at this thing. So that is also symmetric around x equal to 0.5. So since the boundary condition and the initial conditions are symmetric about x equal to 0.5, and the temperature profile that will, or the um, like the profile of u that will be generated after a certain time, that will also be symmetric, because there is nothing that can break the symmetry of the uh, problem, since the boundary conditions are also symmetric and the initial condition is also symmetric, because these two only decide how the profile will be generated in the further times. So one thing now we can say that the u will be symmetric at subsequent times. So what does that means is what does symmetry of the problem gives us that at all times the system is remaining mm, symmetric. So u, let's say 2 comma, this I and 3, like I 2 comma j will be equal to 3 comma j at all times, right, at j, or u 1 comma j will be equal to u 4 comma j, since these two values are equal. Again we have u 0 comma j equal to u 5 comma j. This again comes from the boundary condition itself. So these three conditions will be holding good, because we have a symmetry condition of the problem. So these three conditions will help us actually in getting this value. So now let's put I equal to 1 here. So that will give first of all let's this r is 2. Okay, so now let's put I equal to 1. So what we require is u2 comma 1. Okay, so let's put I equal to 1. So what we have is uh, what we means after doing the algebra, what we will have is u 0 comma j plus 1. So this is what we'll get when we put I equal to 1 and r equal to 2 there. Right. For I equal to 2, what we'll get is e minus u1 comma j plus 1 plus 3 u2 j plus 1 u3 j plus 1 u1 j u2 j plus u3 j. Now we know that the boundary condition doesn't change with the time. Since it's the boundary condition, at all times it will remain valid. So u0 comma j will be equal to u0 comma j plus 1, because I equal to 0 is a boundary condition. So that boundary condition will hold for t j equal t equal to j plus 1, j plus 2, everything, right? So these two are equal. So these two are equal, that I'm saying. So for that, what we'll get effectively is 3 u1 j plus 1 minus u2 j plus 1 equal to 2 minus u1 j plus, and this is equal to 1, the boundary condition that we have here, that is given as 1, right? So that is given as 1. So we'll have these two coming in from these two terms. If we club it, and then u2 comma z. So we have this one equation here. Then for I equal to 2, we know from the symmetry condition u2 comma j will be equal to 3 comma j. That's what we saw here. So this was the condition from the symmetry, right? 2 comma j will be equal to 3 comma j. So what will these two will get cancelled? So effectively what we have is minus u1 comma j plus 1 plus 3u2 j plus 1 equal to u1 comma j. Oh no, sorry. So, and this will this condition will hold at all the time. So u2 j plus 1 will be also equal at 3 u3 j plus 1, right? So these two will give 2u2 j plus 1, right? These two are equal, so 3 minus 1 will be 2. So what we'll have is minus u1 j plus 1, and these two are equal, so it will get cancelled, plus 2 u2 j plus 1 into u1 comma j. So we have these two equation. Now what we require is u2 comma 1 that we require. So for that we require u2 comma 1. So for that we have to put j equal to 0, right? Since we have j plus 1 here, so we put j equal to 0, we have 3u1 comma 1 minus u2 1 equal to 2 minus u1 comma 0 plus u2 comma 0, and what we have minus u1 comma 1 plus u2 comma 1. This is the term that we require, minus u1 comma 0. So we have to find the terms. This is the term we require. We have to find the circled terms to get this u2 comma 1. So we have to find u1 comma 1, u1 comma 0, u2 comma 0, right? So u1 comma 0 and 2 comma 0 basically are the initial, will come from the initial condition, because j equal to 0 is initial condition. So u1 comma 0, yes. So where we have u x comma 0 1 plus 2x. So u 1 comma 0 means x equal to 0.2, so 0 0.20 will give you 1 comma 0, so 2 into 0 0.2, that will give us 1.4, and u2 comma 0 is x equal to 0.4, so 0 0.4 u2 comma 0, 1 plus 2 into 0 0.4 and 1.8. Right? Okay. So what we have here now, 3 u1 comma 1 minus u2 comma 1, 1 comma 0 is 1.4, u2 comma 0 is 1.8, minus u1 comma 1 plus 2 u2 comma 1, 1 comma 0 is 1.4. So we have two variables now, two equations and two variables. So from there you can find u1 comma 1 as 1.24 if we solve this, and u2 comma 1 will come as 1.32. So this is the value that is required. I may have made some calculation mistake, but that's the approach you have to take it. So that comes the option B is the actually the correct answer. So the main I think this type of problems have been shown in the lectures also. Like the problem is symmetric, so we have to take advantage of the symmetric condition, and then write it for two intervals I equal to 1 and 2, like considering what is the value of this thing is required. Usually in exams they will not ask for so many, means like they will not ask like u3 comma 2 or like, because for that you have to solve multiple equations that won't be possible through like by hand calculations. So that's why 2 comma 1 is being asked. So for that we require only two equations, so we took I equal to 1 and I equal to 2. Then we took advantage of the symmetry condition. This is the boundary condition. So once we plug in the values, we get 2 two equations and two variables, out of which one variable is what we need to find out, means the, being asked in the question. Okay. So question number 9, for a derivative boundary conditions. So these derivative boundary conditions are covered in lecture 10 probably. So where if we saw Dirichlet boundary condition, Newman boundary condition, like if the boundary condition itself is given in the derivative form, so how do we discretize it to uh, solve the problem? So this is a boundary condition at x equal to x naught. So we have to find approximate values using forward difference. So what will be the discretized equation that is being asked here? So using forward difference, alpha u. So this is let's say x. So this is x naught and this is x. This is x equal to x naught, and this is x equal to xn. This is x equal to x1. So this is I equal to 0 and this is I equal to 1, right? So using forward difference, we will be taking these two points to represent the derivative. So it will be 1 j plus 1 minus u 0 j plus 1. So this is the form that we get. So once we rearrange the term, we need to find 0 at j plus 1. That's why we represent the time interval at j plus 1 also. So j plus 1 that we will get is alpha u1 j plus 1 minus gamma delta x by alpha minus beta delta x. So this is what we get. So option, I think A is the correct answer. So this is like in a problem, if we have a derivative boundary condition also, so that boundary condition depends like how we use forward difference or backward difference. So it since this is at the initial, we know at I equal to 1, so it's preferable like we use a forward difference. Sometimes if it is at x equal to n, we know at x equal to xn minus 1 the value, so that we can, yeah, so for that we have to use the backward difference also. So I think that is being asked in the second this question also. So same at x equal to xn, so we have to use the backward difference now. So x equal to x naught is here and x equal to xn is here. So I equal to n, I equal to 0. So we have to represent u take these 2 points in the backward difference, these 2 points, which is I equal to n minus x equal to x n minus 1. So u n j plus 1 minus u n minus 1 j minus 1 by delta x plus 1 equal to gamma. So now we need the n j plus 1 term. So if we rearrange, so we'll have alpha u, right? So option C is the correct. So we see, like here we got the value of u at x equal to xn as a function of this n minus 1, means dependent on this node point. Means this is like if we like we earlier have seen all the Dirichlet boundary condition where the value of this u and j plus 1 will be given 0 1 or something, some other values, right? Or we'll have 1 j 0 j plus 1, the initial condition given as this. But now what we are given is like a differential equation itself that is being satisfied at the boundary. So to solve that, we have to discretize it such that it becomes a system of equations along with the main problem. So we see a equation now, the heat conduction equation, del u del t del square u del x square, where x is from x equal to 0 to x equal to 0.5. The boundary conditions are given. Delta x is 0.25, so this is x equal to 0.25. So I equal to 0, I equal to 1, and I equal to 2. Delta t is given as 0.2. Now the boundary condition is being approximated by, so we have a boundary condition here, two boundary conditions. One is u 0 comma t, so that is u at 0 comma j is 0, and the second is del u del x is 8 at x equal to 0.5. So we can say at this point the boundary condition is given by a derivative. So if we represent this by backward difference, what will be the equation that is being asked? So if we represent the backward difference, you so we have to take these 2 points now. We are representing the backward difference. So I equal to 2 and I equal to 1. 2 comma j plus 1 minus u1 comma j plus 1 by delta x equal to 8. So u2 comma u2 comma is x equal to 0.5 tj plus 1. So this will be delta 8 into delta x plus u x equal to 0.25 tj plus 1. So this is 8 into 0.25 x delta x is 0.25 plus u so 8 into this will be 2 plus this. So we have is option B is the correct answer. The a follow-up question of this, the last question, the follow-up question is like we have the same thing. The initial condition is also given for the question. Now we have to find at 0.25 and 0.02. So like this is x equal to 0, x equal to 0.5, and x equal to 0.25. So this is I equal to 0, I equal to 1, I equal to 2. So we need to find at 0.25. So this is the value that we need to find, and delta t is 0.01. So for j equal to 0, t equal to 0, j equal to 1, delta t is 0.01. So we need to find u1 comma 1, that is like that is equal to u 0.25 and 0, no sorry, j equal to 2 will be delta t 0.02. We are asking at 0.02. So we want 1 comma 2, that will be 0.02. So that's the at that node point we need to find out. Okay, so now the boundary condition has to be approximate the backward difference scheme. So what we had is this is the boundary condition that we had. So effectively we can represent it like x equal to 0.5 is I equal to 2, this is I equal to 2. So 2 comma j is 2 plus x equal to, this is I equal to 1, so 1 comma j. Okay, so this is the one of the boundary condition at yeah, this is one of the boundary condition at that is being specified. Another boundary condition is u 0 comma t is 0, so that means u 0 comma j is 0. These two are the boundary conditions that we have. Then the initial condition that is being said is ux comma 0 is 4x cube. So what we have is u I comma 0 is 4x cube. So now let's use the explicit scheme. There is nothing mentioned here. We'll use the explicit scheme. So we'll write the explicit scheme I j plus 1 into r u I minus 1 j plus 1 minus 2 r u I j plus r u I plus 1 j. So this is the explicit scheme. We see the j plus 1th interval is on the left hand side and all the jth intervals are on the right hand side. What we have for r is r delta t by delta x square. So delta t is 0.01, delta x square is 0.25 square, that is 0.16. And this actually shows us that we can use the explicit scheme because this is less than half, right? So the explicit scheme will be stable here. So if you first check the r and C allows us to use explicit scheme. If r would have been greater than 0.5, we would have no option of then choosing the implicit scheme because explicit scheme will not be stable in that case. So now we can also use the implicit scheme here also because it is stable for all r. But since this r value is less than 0.5, we'll choose the explicit because that is less means we have to do less computation there, and it will also be stable for that values, right? So we'll use this explicit scheme. So now we put I equal to 1, j equal to 0. So what we require is I u1 comma 2. So to put this, it will be 1 comma 1 equal to r is 0.16 u 0 comma 0 plus 0.68. 1 minus 2 r will be 0.68. 0.68 u1 comma 0 plus 0.16 u2 comma 0. Okay, so we know this values u2 comma 0 at these are all at initial conditions, right? So j equal to 0, j equal to 0, j equal. So what we have is this thing. So u0 comma 0 will be 0, u1 comma 0 will be 4. No, sorry, u1 comma 0 will be 4 into 0.25 cube, that will be 0.0625. u2 comma 0 will be 4 into 0.5 cube. It will be 0.5, I think. Let's check the calculations. So we know these values at the initial time. So what we get is u1 comma 1 will get the value of 1.0.1225. So these are known parameters at the initial known values at initial time. So we had this. Now we put so what we require is u 1 comma 2. So for that we have to put I equal to 1 and j equal to 1 now. So for that we again, if we write this equation, it will be 1 comma 2 will be 0.16 u 0 comma 1 plus 0.68 u 1 comma 1 plus 0.16 u 2 comma 1. So 1 comma 1, this so what are the known values here? This we know, u 1 comma 1 we just found out. This to find this 1 comma 2 we need u 0 comma 1 and u 2 comma 1. So 0 comma 1 is a boundary condition. So we saw 0 comma j is 0, so 0 comma 1 will be 0. So this is 0 boundary condition. Then u2 comma 1 is also a boundary condition. With boundary conditions, how did we get it? u2 comma j, u2 comma j is 2 plus u1 comma j, right? So I'll write here u2 comma 0 boundary condition equal to 2 plus u1 comma j. So put j equal to 1, u2 comma 1 will be 2 u1 comma 1, and 1 comma 1 we know, now we have found out here, it is 0.1225, so it will be 2.1225. So these two values we got, this already we had found out earlier. This is the boundary condition, this is the boundary condition. So using putting all those, what we'll have is 0.16 into 0 plus 0.68 into 0.1225 plus 0.16 into 2.1225. So this will give us 0.4229. So this is the value of the u at x equal to 0.25 and t equal to 0.02. So this is what I had for today's session. Thank you for attending. Yeah. If you have any questions, you can ask, or we can just close it.
Sir,
Yes.
sir,
Yeah.
can you tell me the reference book or what book you have to refer all these things? That is what the notes you have given in the class
Yeah.
video lecture. That is enough for that.
That should be enough for this means for this assignments and all, but for learning more I think you require.
You have to do that some more.
Yes. I don't, I right now I don't have any name for any reference, like I have to search and tell you. Then maybe next class I can say.
Because one each and every problem you are doing different way. One is explication, another interpretation, then you have to do it in a transfer section, then
Yes.
boundary condition.
Yes.
So all problems are different.
Yes.
So because everything is coming from the
Yeah.
You should have you have taken only the heat equation, I think.
Because this week 2 is based on the parabolic equation, so that's why the heat equation being used. That's a form of the parabolic equation. Then week 3 and week 4, I think the professor will deal with elliptic equations and wave equation. For that you will see some Laplace equation and then Poisson equation or something like that. For that, this heat equation being, this is like a example of a parabolic equation. So this will be more or less same like any parabolic equation you take. This will be of this form only. Some constants here and there will be varying, but that you can account it for.
Thank you very much,
Okay.
sir.
Okay.
Very
Welcome.
useful for me.
Okay.
I
Welcome.
got to learn so many things. Thank you.
Welcome.